Okay, so this is where we left off from yesterday, I think. We were going to classify these things as, are they strong, are they weak, that sort of thing, okay? Oh, wait, no. We got to do the practice first. It skipped over these. There we go. Why is it doing that? There we go. We are doing a lab today. We're going to just finish. We've got 2 slides to finish real quick, and then we'll start the activity. And I'm going to have some stuff to explain to you as far as the activity is concerned. Okay. So, using what we hopefully remember from yesterday, we're going to identify these as either strong or weak acids or bases. That may or may not work. Did it work? No. Ernst has one that works next door. Okay, so we're going to identify these as being strong or weak acids or bases. And I want to do a little something extra with this that I think will prepare you for the homework I'm going to give you, which is we're going to talk about, okay, how would we write the dissociation reaction for each of these? And we'll talk about that after we classify them, okay? So we'll just use a simple system here. SA is strong acid, WA is weak acid, SB is strong base, and WB is weak base, okay? So for the first one here, the HNO3, first of all, acid or base? How many of you think acid on that first one? How do we determine whether it's an acid or a base? Okay, it's pretty easy with an acid, right? Because all you're looking for is the H out in front, okay? So that's going to tell us this one's an acid. Now, is this a strong acid or a weak acid? Oh, how do you know? Okay, there's only one way to know whether it's strong or weak at this point, okay? Now, in AP Chemistry, you learn some different ways to figure this out. But as of right now, there's only one way to know whether it's a strong acid or a weak acid. What is that? You have to memorize them, okay? I gave you that list of 7, remember? If it's not on that list, it's weak, okay? But HNO3 is on that list, so it is a strong acid, all right? So we'll just put an SA right there. FeOH3. Okay, that is a base. Yeah, see, I'm not happy with that. Okay, here's the deal. We'll go ahead and classify that as a weak base because it's not in group 1 or group 2, but the reason that this is weak, it's not really weak by the definition of weak. Anytime that this dissociates, it's going to completely dissociate, okay? The thing with FeOH3, iron hydroxide, it doesn't dissolve very well in water. So that's why it's not a very good base, because it just kind of sinks to the bottom and sits there. It doesn't really dissolve, okay? So we'll call that a weak base, I guess. I'm not real happy with that. I won't give you one like that, okay? CSOH. That's a base, definitely, because of the OH, right? Now, okay, how do we know if it's a strong base? Do you remember? If it's something in column 1 or column 2, except for the BE and the MG, those are the 2 exceptions, okay? But CS is in the first column, right? So that combined with OH, that's definitely a strong base. Okay, next one down, HC2H3O2. That's an acid. Strong or weak? How do we know it's weak? Because it's not strong, okay? So weak acid. HF? Okay, yeah. Now, again, hydrofluoric, remember it eats through glass, but it's not a strong acid. Kind of weird, right? But it's not, strong or weak doesn't have to do with how reactive it is. It has to do with how much it dissociates when you put it in the water, okay? Because this doesn't completely dissociate. This is a weak acid. It's not one of our 7. CuOH2. Yeah, and again, okay, we'll classify it as weak, but it's not, when it dissolves, it completely dissociates, okay? But it just doesn't dissolve very much, okay? Copper hydroxide, again, you put that into water, it's just a blue solid that sinks to the bottom and doesn't really do anything. It doesn't, not much of it dissolves in the solution, okay? H3PO4. That's a weak acid. KBr. Strong base. What's going on there? Okay, well, let me ask you this question. Is it possible for something to be neither an acid or a base? Is that possible? Okay, we've actually dealt with a lot of chemicals this year that aren't acidic or basic. All right? There's no H in here, so it's not an acid, right? There's no OH, so it's probably not a base either. So this we're going to call, this is the tricky one. This is neither. Okay? Not an acid or a base.
Are you going to go with one like that?
It's
How do
possible.
you know that it's neither?
Well, because it doesn't have an H or an OH. Yeah, right? All the rest of these, either an H at the beginning or an OH at the end, right? All right, H2O. Good, remembered that from yesterday. You guys remember H2O can also be written as HOH, so it can act as both depending on the situation, okay? All right, NaOH. Strong base. Good. Okay, so let's take an example of one of each of these and just practice writing the dissociation reaction. Now, again, what do I mean when I say dissociation? Well, not necessarily that it dissolves. When it does dissolve, what happens to it if it dissociates? It breaks apart, okay? Now, it's important to understand the distinction there. Sugar dissolves in water, but it's a covalent compound. It's not ionic, so it doesn't break apart, okay? Sugar is C6H12O6, right? That does not break apart when you put it in water, but it does dissolve. So dissolve and dissociate are two different things, okay? So a strong acid, remember, completely breaks apart, completely dissociates, right? So let's look at HNO3. How would I write the equation for that dissociating? H plus plus NO3 minus, right? And that's it. That's all there is to it. Pretty easy, right? How about a strong base? Let's pick a strong base on this list. CSOH, okay. That's going to dissociate into CS plus. Now, how do I know CS is just a 1 plus? Yeah, two ways, right? It's in the first column on the periodic table, so it's going to be a 1 plus. But it also combines in a 1-to-1 ratio with the OH. And we know from our polyatomic ion chart that's a 1 minus, right? So if it's a 1-to-1 with a 1 minus, then it must be a 1 plus. So CS plus OH minus, okay? Again, you could put aqueous on all of these for the states of matter, but I'm not going to be all that concerned with that. Okay? Now, let's do the weak, let's do the weak ones. So the weak acid. Okay, HF, I like that one because it's short. What's the only thing that's different when I'm writing the weak acid equation? You write the equilibrium arrows. You guys remember that from yesterday? Only for weak. Yes. H plus plus F minus. Okay? So everything else is the same. The only thing that's different is you put your equilibrium arrows, because what does that show us? It doesn't completely dissociate, and it goes back and forth, right? So some of the HF is breaking apart at the same time the H plus and the F minus are coming back together to form HF. Okay? There is not a good weak base on this list that I'm happy with, so I'm going to give you a different one. And I will tell you, weak bases are the hardest out of all of them. Okay? A good example of a weak base is NH3. Now, this is going to help you on your homework, because one of them that I put on your homework is NH3. So you might jot this down somewhere. So NH3 is a weak base. Now, how can I tell that's a weak base? Because it doesn't have OH minus in it, right? That's what makes the weak bases a little bit tough. They don't always have OH minus. Now, the only weak base I'm really going to hold you responsible for is this one. Okay? So if you just remember this one, you'll be fine. Does that make sense? I'm not going to ask you this. I'm not going to ask you this because in my mind, those aren't really weak bases. Those are things that are bases when they dissociate, but they just don't dissolve enough in water to really raise the OH minus concentration of the water. Okay? This is a true weak base. Now what it does, I don't think we talked about this. Did we talk about this yesterday? We might have talked about this yesterday. Okay. This is the one example you really do need to know for weak bases. Okay? What happens here, remember, a base is something that will make more OH minus in the solution, right? Okay? So this NH3, and you can actually look at the, just in case you're interested here. This is the Lewis structure for NH3, right? We drew that one a lot when we were drawing Lewis structures. Now notice, there's a couple of free electrons here, okay? So if an H plus is floating by, you think it might be a little bit attracted to this right here? Okay, because remember, H plus is just a proton, okay? So it's looking for some electrons that it can connect with, all right? So this H plus comes by, sees this lone pair of electrons on the NH3. That's what makes the NH3 a base, because it's going to grab a hydrogen from something else, okay? So in this case, it's going to grab hydrogen from water. Let me write the water like this. You might be able to see it a little more clearly here, okay? In that case, is water acting like an acid or like a base? It's giving away an H plus, right? So it's acting like an acid in this particular case, okay? Now again, this is as tricky as yeah, hopefully that makes sense because it's just this hydrogen is moving from one place to another, okay? Why did I put the equilibrium arrows? Because it's weak, right? Because it's a weak base. So you just got to remember, you write the equilibrium arrows when you're dealing with a weak acid or a weak base. You write just a forward arrow when you're dealing with a strong acid or a strong base, okay? Yeah, sure. Actually, I'll go ahead and pass out the practice problems while you guys are writing that down if you need to.
Thank you.
Mm-hmm. You're welcome. Wow, you guys are very grateful today. This is the most grateful I've ever had students be for homework. I like it when students thank me for tests. It's kind of funny, you know. Thank you for this test I'm about to take. Okay, so real quick, one more slide that will kind of set us up for our lab, and then we're going to get started on the lab, okay? Everybody ready? We good here? Okay. All right, so strong, weak versus concentrated and dilute. We need to know the difference between those two, okay? If something is concentrated or dilute, that means how many moles, okay, or the number of acid or base molecules is another way to say that, dissolved in a certain volume, okay? To measure concentration, we use molarity, right? Molarity is moles over liters, okay? So I don't know if you guys remember this. When we were talking in the solutions unit about Kool-Aid, we talked about strong Kool-Aid versus weak Kool-Aid. Another way to say that is concentrated Kool-Aid versus dilute Kool-Aid, right? So if it's concentrated, there's just more of the Kool-Aid in the water, okay? If it's less concentrated or more dilute, then there's less Kool-Aid in the water, okay, and it's not going to taste as strong. That's the concentrated or dilute idea. Now, I already said sugar doesn't dissociate, right? So this has nothing to do with if it's strong or weak, okay? So in other words, I can have a concentrated strong acid, okay? For example, if I have 1 molar hydrochloric acid, that's fairly concentrated, right? But I can also have a dilute strong acid if I had like 0.01 molar HCl. Still a strong acid, right? But this is dilute, this is concentrated. See the difference? Does that make sense? Okay, so that's the concentrated versus dilute thing. Strong or weak refers to how much it dissociates. Okay? So you just need to understand the difference between those two. We're going to do an activity right now that will hopefully help with that. All right? Is that the only thing on that slide? I think that's... Oh, no. It's possible to have... Yeah, I said that. Dilute solution of a strong acid. Or a concentrated solution of a weak acid, right? Can go either way. Okay, that's it. All right, so I'll go ahead and stop the notes. We'll get started on this activity now. Hopefully you guys will have fun with this.